Hello and welcome back. Contour integration again. Today's it's not going to be just a lecture, but I'm going to do a little bit of a talk and analysis about just this kind of stuff and just show you a few things which we take it for granted that we understand and we know until we try something. The integral in question that we're going to use is actually the integral of from 0 to infinity of 1 over 1 plus x to the 6, which can be done, of course, with real methods. In fact, I have actually done this using further maths. It's actually quite disgusting. It's using the cross twins, and it's a nightmare, but we're going to do it with contour integration. Before we do it, the way I'm going to show you, I'm going to actually quickly discuss the way this is done in practically every book and every lecture that I've come across. And what of course you will do in there is you will consider, of course, the integral of 1 over 1 plus z to the 6 dz. And what contour will you be using for something like this is the semicircular contour on the top half of the complex plane. Of course, the rationale is your real bit is going to come from the x-axis 0 to infinity. That is, of course, an even integrand. So you're going to get, of course, from minus infinity to infinity once you let r equal to once you let r goes to infinity. The contribution around this gamma 1 is very, very easy, very standard to show that is actually 0, and of course the integral will appear. The problem with this particular method, which I personally do not like, is you have way too many poles inside this semicircle. I mean, if you think about the roots of unity, z to the 6 is equal to minus 1. Quickly, I'm not going to write them down, but just so you can get an idea, z to the 6 is equal to minus 1, so it's going to be e to the I pi. So you're at 180 basically. Divided by 6, it'll give you 2 pi over 6, or 30 degrees. So you're going to have a pole at 30 degrees here, e to the I pi over 6, and then you will have more poles every 60 degrees. So you're going to have another one on the imaginary axis, another one at 150, and of course another 6 which are outside. We don't care, and I don't particularly like to find the residue of 3 poles from something like that. I mean, you're gonna have to use L'Hopital's rule and all sorts of stuff. It's very, very messy. I don't like it. Okay, and there's one more consideration to actually discuss, and this is the lecture that I'm going to mention because of course I'm going to use it. Is, you know, when we're saying, okay, this is my 1 over 1 plus z to the 6 dz, and we're getting the parameterization along the real axis, we just say, well, blah blah blah, z is equal to x, and therefore my dz is equal to dx. Is not quite true, although it doesn't really matter in general as long as you don't have fractional powers or logs. So this is actually true, but in reality the parameterizations that we should be using for this section here, your z is not just x, it should really be, x is the modulus, so it should be x e to the 0 I, and that's the argument, of course. So this is the parameterization, and you're going to let, of course, x run from 0 to r or to infinity when you take the limiting case, while on this particular section, when you're on the negative axis, your z is not x again, is in fact modulus x e to the I pi. The reason it doesn't matter if you don't have logs and fractional powers is because, of course, that is a minus 1, and when you differentiate it, you're gonna get another minus 1, and eventually, if you try it to go and do it very, very formally, you're gonna end up with exactly the same thing as if you said z is x on the whole thing and your dz is equal to dx. So in this particular case, we tend to ignore it, but today we're going to see a case where this is not ignorable, and we have to be careful when we set it up. And as I said, careful even on the x-axis, unless we have if we have fractional powers or logs, this is not true. Z is not equal to just x. Okay, so let's look now into how we are going to do this particular integral. Again, as per usual, I forgot to check the answer, what answer I should be getting for something like this. I'm expecting something pies in there, but I don't know, so I hope I do it correctly. All right, what integral we're going to consider? We're going to consider, of course, the integral of 1 over plus z to the 6 dz around a gamma, but my gamma is not the semicircle that I put up there. I can use it, no problem. In fact, I think in my book I actually do use the semicircle, but I'm going to use something completely different today. This is now my contour, and I will try, I'll make an attempt to actually do a bit of teaching. I haven't taught this for a very long time. Sometimes I'm not explaining things very well. This is now your complex plane. Try to give you a bit of rationale if I can, because it's not that easy to explain this bit. The contour that I'm going to use is going to be a sector, which is something like that. Okay, and how, well, the radius will be r, so it's of radius r, and let's put, this is im z, cannot fit real z there, hope you let me. And I'm gonna go around it in anti-clockwise direction. The question is now, how big is this particular angle of my sector? I need to have it as pi over 3. I'll try to explain a little bit why I want it to be e to the pi over 3 is because when I'm going to parameterize later on this straight line segment, which is not just z is equal to x anymore, you will see in a second what's happening, but this is now I'm doing it before I actually see it. I'm going to parameterize and say z along this line here is going to be x e to the I pi over 3. And the reason I want to do something like that is because when I put it to the power of 6, it's going to give me, of course, the x to the 6, which I'm after here, but also I'm going to get e to the I 2i pi, if you want, in which case I've got a 1, so I don't have to worry about it. Any other angle will not do. Okay, of course I could go all the way around and go pick up my integral from the real axis I've just explained there, but then I have 3 residues which are very, very ugly to compute. So I'm going to use this particular contour. So the only thing I need to define up there is perhaps this is going to be my gamma, little gamma, and let me use a blue pen. I don't know if blue pen shows in my videos. It looks very dark, practically the same color as black, and my gamma is the entire triangular structure. Well, of course not the triangle, it's a sector. Okay, what residues, what poles do I have? The 1 plus z to the 6. It makes the denominator equal to 0 quite clearly. Z to the 6 is equal to -1. And the roots of, the 6th roots of -1 is of course e to the I pi, with multiples of course, and if I divide by 6, the first solution is going to be at e to the I pi over 6. In other words, at 30 degrees, so that's a 60-degree angle, so it's actually exactly halfway on the angle by sector. Somewhere here is a pole of I pi over 6, and of course the next one, because they're equally spaced every 60 degrees, it'll be on the real axis as I just explained earlier on. So this is the only pole which is inside my big gamma. Okay, so I guess I'm going to use the residue theorem as per usual, and I'm going to say this complex integral is of course 2 pi I times the sum of the residues of the poles inside my big gamma. So it's only one pole. I'm going to find this residue. It's a simple pole. So the limit as z tends to e to the I pi over 6. And standard formula, z minus e to the I pi over 6. Multiply my f of z, where my f of z is of course this. Times 1 over z to the 6 plus 1. Of course I can factorize this into 6 brackets, z minus e to the I pi over 6, z minus e to the I pi over 2, z minus e to the I 5 pi over 6, and so on, going around the circle, and cancel my bracket and take my limit. It's just a mess. So this is of course a 0 over 0, so I can use L'Hopital's rule. That's the standard way with expressions that are as ugly as this. So this is on the top, of course. So if I differentiate the numerator separately, I'm going to get a 1 from just a z. And if I differentiate that, I'm going to get 6z to the power of 5. So that's an easy limit to take. So this will now give me 1 over 6 e is to the power of 5. So it's going to be I 5 pi over 6. And let's write a little bit better as 1/6. And I'm going to put the exponential as a negative minus do watch me. I'm the king of the mistakes in there. So I'll make it that. My handwriting doesn't help sometimes. So this is the residue of that single pole that I've got. So I'm going to write it here straight away. Is equal to 1/6 e to the minus I 5 pi over 6. And I'll do the tidies at the end or at a later time. At the moment, I'm just going to do my integrations and see what happens now with this particular integral. Okay, so as per usual, I'm going to now split into 3 separate sections and carry out my integration. So I'm going to say curly bracket, integrating from, let's start from here, from 0 to r. And it's very difficult to actually explain which one it is. Maybe we should have actually called it gamma 1, gamma 2, gamma 3. So the first one is along the x-axis. Okay, and actually let's call it, because it's very, very confusing otherwise. Let's say this is now our gamma 1, this is our gamma 2, and this is our gamma 3. Okay, so let's lose the limits there. So that's the integral around gamma 1 plus the integral around gamma 2. Easy to write as well, don't have to look at limits or anything. Gamma 3 of f of z dz is, of course, by the residue theorem, equal to that. Okay, my integral, my real integral, not to infinity, will come from these straight line segments. This particular one, I can see and I can justify to somebody who has done loads of this in 3 lines why, as r tends to infinity, there's 0 contribution for that. But for us, we're going to do it properly. So we're going to show that the integral around gamma 2, that's the circular arc, as we blow it to infinity, as we blow the r to infinity, has 0 contribution. So this is an estimation. Very, very standard working. We've done loads of this, so I'm going to do that very quickly. So the integral of 1 over 1 plus z to the 6 dz modded around gamma 2. I'm going to parameterize. I'm going to do that here. Around gamma 2, my z is, of course, r e to the I theta. dz is I r e to the I theta d theta. And my theta will run, actually I prefer not to put it like that, because there's no sense of direction when you write like that. It will run, theta runs from argument 0, from 0 to pi over 3. So these are the particulars. So we can parameterize now 0 to pi over 3. And putting our stuff in, we're going to have 1 plus my z, looking at the parameterization that I've done in there, it should be, of course, r to the 6 e to the 6I theta. Looking at this bit here, my dz, I'm going to get you to take a ride on the top, so I have less to write. Let's write the d theta bit on the outside, not on the outside, outside the fraction rather. And on top of that, I'm going to have an I r e to the I theta. Okay, then the standard inequality, which says, of course, the modulus of the integral is less or equal to the definite integral of the modulus of the integrand. I put pi over 2 there. Why? I will never know. It should be pi over 3. That's the mistakes that I make, and then I pull my hair, try to look for them. Okay, what am I? Am I taking mods now? moving on the inside, IR e to the I theta 1 plus r to the 6 e to the 6 I theta. This is a standard result. Look at previous lectures of mine. I have gone in a little bit more detail than what I'm doing now. Of course, afterwards, that is, of course, let's use red pen, the modulus of the top over the modulus of the bottom, standard rules of the modulus in real or complex. And then, of course, another fact after that, if you have multiplicative quantities, you can take individual moduli. Again, all standard stuff. I cannot fit another line there, but it's modded. Okay. And of course, here I cannot do it because of the plus. So I continue from this line that is equal to 0 to pi over 3. The modulus of the modulus of y is 1, so that's, I'm not going to write. The modulus of r doesn't even have a modulus signs because it's always positive. E to the I theta, we mentioned several times, is 1. E to the I something real, always 1 when modded. And I've explained in lectures in the past the why it is. You can check it yourself. And at the bottom, of course, I can't do anything. 1 plus r to the 6 e to the 6 I theta d theta. Then I'm going to write this inequality because, of course, this is very important. We don't really need this anymore, so let's take it off. The inequality is part of the triangle inequality group. Is the z plus w modded is is greater or equal, sorry, I do apologize, I'm having a really bad day today. My apologies, is greater or equal than the mod of z minus the mod of w. And of course, it could be the other way around because, of course, there's nothing special about z or w. So we could have written it either way. And the way, without loss of generality, that I'm writing it in there is such. So this modulus is bigger than this modulus. So both sides at the moment are positive, which allows me to reciprocate it and say quite clearly 1 over the mod of z plus w is less or equal now. It reverses the inequality to this. This is a standard inequality used in estimations in contour integration an awful lot. So I'm going to use it on this bit here. This is my z and this is, of course, my w, or the other way around, doesn't really matter. But I can certainly say now this is less or equal to the integral from 0 to pi over 3. The r, leaving my alone on the top, is quite happy. And now I can say it's the modulus of 1, quite stupid to even write that, minus the modulus of r to the 6 e to the 6I theta modded d theta. So that's just merely using this inequality. That's my z and that's my w in there. Why did I do that? I hope this part of the board is still visible on the video. That will be a check, so I must remember when I watch it afterwards just to check. So I'm going to try to write a little bit smaller just in case. So this is equal, I'm going from this line here, 0 to pi over 3, r on the top, modulus of 1 is of course 1. And now this, again, I can take, because multiplication, I can take individual moduli, the mod of r to the 6 times the mod of e to the 6 I theta. The r to the 6 a positive quantity, and therefore I don't even need modular signs there. And e to the 6 I theta is I real, and therefore when modded, this bit here will give you 1. So it's times 1 d theta. And of course, now this quantity is a constant, not a constant independent of theta. So I can pull it outside the integral. It doesn't really matter whether it's 1 minus r to the 6 or r to the 6 minus 1. It will hardly matter because, of course, when I take the limit, that will be gone. So that's 1 d theta. And how annoying, I ran out of space just to write 2 lines. So I'm going to put it up here. So let's make a little bit of room. These estimations normally in this kind of work are the bits that take most of the time, but they're actually quite tedious. I did say they look daunting the first time you do it. If you do about, I don't know, 10, 15 of these, not of course exactly the same one, you realize that they're practically the same. It's just regurgitating the same material. Now, I've gone here because I had less or equal throughout. I need to maintain one of them. So that's going to be r over 1 minus r to the 6. And of course, integrating 1 d theta from 0 to pi over 3 is times pi over 3. And quite clearly now we can see that as r tends to infinity, this will vanish, or we can put an extra line. This of course is of the order capital O 1 over r to the 5, this particular term, and therefore this will tend to 0 as r tends to infinity. So what we've shown here is, in the limiting case, as r goes to infinity, there is nothing coming from gamma 2. Okay, we're not going to need this inequality. Very important. I keep writing this. This is one of my things. I think that this is very important because when I was learning this kind of stuff myself, I struggled a little bit with this one. So I want to make sure it goes in. Okay, so now we're going to see what happens as r tends to infinity. What happens to our integral? Okay, first of all, as r tends to infinity, we're going to have the integral around gamma 1. And what is the integral? So I'll parameterize it at this stage. Let's leave it as that. So I'm going to write it 1 over 1 plus z to the 6 dz. So this is along the x-axis plus the integral around, not gamma 2, this is now gamma 3. Gamma 3 is, of course, I'll label that, of 1 over 1 plus z to the 6 dz is, of course, equal to, let's tidy this a little bit perhaps, this is going to be pi over 3 I pi, there's a 9 there, I pi over 3 e to the minus I 5 pi over 6. Okay, we're going to need to parameterize now the gamma 1 and gamma 3. As I always say, if you're on the x-axis, and I mentioned in the beginning, of course, particularly the positive x-axis, you can actually say z is equal to x. Of course, it should be x e to the 0i, which of course is 1, and then your dz, which is going to be, of course, dx e to the 0i, and it doesn't really matter when you put to the power of 6 here. Okay, it's still going to be 0 there, and of course it makes absolutely no difference. Quite strange to start doing things like that there. Okay, so this is now the parameterization along gamma 1. So that's our gamma 1. How are we going to do now the parameterization along gamma 3? Z is not equal to x. You have to be very careful there, definitely not x. So the complex number now, when it's running along this path, okay, is going to have modulus x, some number, okay, you can use t if you want, doesn't really matter, and of course its argument is going to be along this line here, pi over 3, so it's going to be pi over 3i. And the limits, of course, here, okay, I didn't put the limits. The limits will go from, as we already said, as r tends to infinity, along gamma 1, it'll be going from 0 to infinity, 0 to infinity. However, let me just do the dz first of all. Dz for the gamma 3 is going to be dx e to the pi over 3i, and the limits, imagine that has been blown to infinity now, it'll be coming from infinity to 0. So you have to be careful in a lot of fronts. And I didn't say necessarily this is an easier way compared to the original approach to this with the standard semicircle. It's just that I want to kind of give you a better idea about these parameterizations and what you can actually do. Okay, so let's start putting things in carefully, because we don't want to make mistakes now. So for this particular one, it's of course very nice, 0 to infinity, 1 plus x to the 6 dx. All I've done is I've just put that that's my gamma 1. For the other one now, the limits first of all are from infinity to 0. I can easily swap them by creating a minus. Now, this is now why I picked the slice. I did mention in the beginning, is because if you look what happens here, I'm going to write it in full, of course, x e to the I pi over 3. When you raise it to the power of 6, you're still going to get 1 plus x to the 6. Okay? Even from a slanted line like this, because of course that's going to give you e to the 2 pi I, which is 1, and you're done. Because it won't quite fit in there, I'm going to get the dz to take a right on top because I only got a 1. So on the top of that, I'm going to have e to the I pi over 3. And of course I've got my dx. Let's leave it a little bit further away. And that, of course, is going to be I pi over 3 e to the minus I 5 pi over 6. Okay. Let's do a bit of a tidy. This one, of course, is going to be like that. There's nothing to do on the first integral. 1 plus 1 over x to the 6 dx. Let's do a couple of things for this particular one, and let's make sure we don't make mistakes now. First of all, I'm going to swap the limits. So I'm going to put a minus on the outside. So the limits have gone as 0 to infinity. I left some space there because I'm going to pull outside the e to the I pi over 3. That's this constant here. That's gone outside with a minus. This is my 1 now on the top, and of course this is going to be 1 plus x to the 6. Of course e to the 2 pi I is 1, and this is all good so far, and it's equal to that. And I hope now I'm gonna get my answer. Oops, 5 pi over 6. Room needed. So, do I need the parameterizations? Not really. Let me just take them off. When I see a full board, it really does annoy me. I wish I had a bigger board. But board's like a sponge. The more you have, the more you use inefficiently, and you're never going to have enough. Okay. As that tends to infinity, we don't need it. Shall I take off this line as well? Let's take it off. Hopefully I have copied it correctly. The problem with me is I have some kind of disease, if you want, that I copy all sorts of weird things from one line to the other, so I don't trust myself. All right, now putting these two things together, 1 minus e to the I pi over 3, factorize out of this integral, 0 to infinity, that's this bit here, 1 plus x to the 6 dx. That's my integral to be found, and that is equal to I pi over 3 e to the minus I 5 pi over 6. So now it's a final tidy from all of this, and from here I'm going to divide by the bracket in front of my integral. I have isolated now my real integral, 0 to infinity of 1 over 1 plus x to the 6, to be equal to this mess. So how I'm going to write this? I'm going to write it as I pi, let's put the over 3. I'm going to write it as follows. This is this bit here. Then I'm going to write times, put the exponential on another fraction, and then this bracket divide underneath there to keep track of my stuff. I hope it's all good there. So next line from there, I'm going to create some kind of hyperbolic, complex hyperbolic from that, some hyperbolic shine by the looks of things, by doing the following. I pi over 3, factorize e to the minus I pi over 6. Let me write it and then see, we'll check it. This one now needs the positive exponential. I pi over 6, so that's your 1, minus, from 60 we took 30, so we've got another 30. I do think in degrees, although I write in radians. I'm sure many of us do. So I pi over 6, so that is, wait a second, something's not quite right. I factorized, no, I'm going to factorize a positive e to the I pi over 6, so that's going to go negative, so that's still 1, okay, and now pi over 6 and pi over 6 gives me pi over 3, so I want it like that. I was hoping to get the sign the right way around, but I'm going to have to have a minus there, annoyingly. So e to the minus I lost a 5 there, wasn't a 5 there? Yes, it's up there, luckily it's up there. That's what I mean about copying wrong from line to line. I can't help myself. All right, so equal I pi over 3. Couple of things. First of all, these two exponentials. That when I go to the top is going to go minus. So it's going to go minus 5 pi over 6. Minus pi over 6 is minus pi. That's 150 in degrees. That is 30 in degrees. 150 take away, minus 150 take away minus 30 is minus 180. So it's e to the negative I pi. Okay, if you're having a calculator, you can actually do it on your calculator. So this is these two bits together. Okay, and this one, if I factorize a minus out of these two, I can swap them around now. So it's going to be e to the I pi over 6. That has the plus, and the other one has the minus. So now that's a sign. Minus I pi over 6. Close bracket. This is still going, very annoying. When I get out of the board in a minute. All right, so that's going to be equal to I pi over 3. E to the I pi or minus I, e to the minus I pi is minus 1. So that is a minus 1 here, this exponential. And this quantity is another negative here. And we got two lots. Because of course normally for sine or cos we need halves there, so we've got two lots, and that is the sine, let me just get out of the way, the sine of I pi over 6. Let's just check it very quickly. Yep. All right, couple of things. Let's lose the minuses. These have gone. I'm gonna have I pi over 3. The minus I don't really care. I could have put over 6, but I'm going to get another half from when it becomes sine of pi over 6, so I'm going to leave it as a 2 there. The minus is gone, so it's a plus, a 1. And the sine of I pi over 6, of course, the same as the sine of pi over 6, but the I comes to the front. And that will give me something real. The question is it the right thing? That I don't know. It's going to be, of course, I pi over 3 times the sine of pi over 6 is a half. 2 times a half is a 1. So that's 1 over I, which of course it'll give me pi over 3. I do apologize. I hope this is the right answer. I'm very, very annoying at times. I keep saying to myself, next time, please check the answer before you do the lecture, and I always forget. So what I've done in principle is correct. I might have made a mistake somewhere, and I haven't carried a factor of 2. Please forgive me for that if I have done so. I made it pi over 3. It's at least real, so we haven't done any conceptual, I'd like to think, mistake in here. But I hope you followed, more importantly, the rationale why for this I chose a slice like this, the pi over 3 angle. I mean, it just sounded quite arbitrary, but it wasn't. It's because of a lot of reasons why I did so, and that's a different way. You will not find this in books, but it's worth exploring, and I hope it gives you better understanding into this particular and beautiful, I think, part of maths. Okay, I'll see you very soon. Who's laughing now?